In this video, we'll be looking at the concept of volume by revolution using disks and or washers. This first video, we'll go ahead and follow the steps of what we should be doing in order to be able to identify the object that we're trying to find the volume of, and then we'll go ahead and integrate that particular space. So, the first step is determine the volume of the solid obtained by rotating the region bounded by y equals x, x equals 4, and the x-axis about the x-axis. So it's important to notice that this x-axis is not being said twice for no reason. We're looking at the region bounded by these three equations. Okay, so the first step is I'm going to go ahead and draw that space. Y equals x is this line right here. X equals 4 is this line right here. And the x-axis is this line right here. And again, we're looking for what space is being enclosed by all three of those equations. And that's this space right in here. Okay, so I'm going to go ahead and draw those vertical lines. Now again, it might be horizontal, it might be vertical, it entirely depends on the which way that we're rotating it. So now, it says determine the volume of the solid obtained by rotating this region, so this space right here, about the x-axis. So I want to take this object and I want to rotate it around the x-axis. So the concept that I'm going to do here is I'm going to go ahead and redraw this object without all those extra pieces to it, okay, without all those extra unnecessary lines. So when I draw this triangular piece, I'm going to go ahead and rotate it around the x-axis, which means I'm going to go ahead and copy it to the best of my ability so that it reflects perfectly over the x-axis. And then I'm going to go ahead and draw myself some circular cross sections that appear to be, again, what create it. Now, in terms of this, you'll notice every vertical cross section I make is some form of a circle. So this right here is actually the object that is a cone. Now, not all the objects that we do in these types of problems will always be something we can identify or label. But in this case, we can label it. Now, a cone, remember, again, is nothing more than circular cross sections creating the overall end space. So the idea here is this. I need to, once again, just like the volume by attachment, I need to integrate some kind of area function. Okay. I'm also going to note that I'm going to integrate this in terms of dx. Now, it's not always going to be in terms of dx. Sometimes I might cut it in terms of dy. But if I cut it in terms of dx, you'll notice that back in this region right here, if I can figure out this location right here, I can cut this region up until I get to this location right here, which we know this is right here x equals 0, and this right here is x equals 4, based on the, again, equations we were given. Y equals x intersects the x and y axis at x equals 0, and x equals 4 intersects that line at x equals 4. So, that tells me that I'm going to integrate from 0 to 4. Again, I must integrate in this region, in the provided region. That's where I have to actually integrate. Now the question is what is the area of those cross sections? Well, each one I cut here, this provides me a length, and I don't want the area of this space, I want the volume of this space. So let me go ahead and take one of these cross sections, and I'm going to go ahead and darken it in. That cross section right there is what the actual area of each slice I want to play with is. Now that just happens to be the area of the slice at a given x value. But notice if I go ahead and darken in a different location, the cross section is just a larger version of that. Okay? It's important to note that there is a radius to that circle, and that's what that cross section is. Again, the cross section that we're looking at is actually a circle. So if I look at the area of a circle, again, the area of a circle based on this detail, the area of this circle based on that detail, the area of this circle, all of those circles will have an area based on the radius. And the area of each of those is going to be pi r squared. So we've done something similar to this by attachment, but now we're going to go ahead and do a whole circle where you'll notice each of these vertical lines coming down from this circle is nothing more than the radius. But each of those vertical lines is nothing more than the distance from here up to here. So this distance right here is nothing more than the y value, okay? And very carefully I can identify that the area of each of these circles, depending on the x value that I'm selecting from 0 to 4, will have an area of pi times r, r being the distance of y here, squared. But note, again, that my integral is in terms of dx. So that means that this area function must be in terms of dx. Well, what is the formula for y in this system? Well, that distance y is nothing more than y equals x. So that's the equation that's going to replace that system. Okay. In that case, I'm simply going to integrate x equals 0 to 4 of pi r squared dx. This, again, one more time, is the method of disks. The reason why it's called disk method, again, the reason why it's called disk method is because every single one of these cross sections, every time I rotate an object, it will create these nice circular cross sections. And those circular cross sections will have an area of pi r squared. So I'm doing nothing more than integrating the formula of pi r squared every single time, where r, depending on how I'm cutting it, if I'm cutting this vertically, my r is actually going to be f of x, the function. Okay, so this right here is the actual equation or integral to evaluate the area of this cone. So to do so, we're going to go ahead and do that. I'm going to do it down here. We have the integral of x equals 0 to 4 of pi x squared dx. I'm going to simplify that. We don't need that parenthesis in there anymore. I'm going to note that if I integrate this, pi is just a constant. It can be pulled out of the integral. So I have pi integral of x equals 0 to 4 of x squared dx. When I integrate this, I'm going to have pi times the integral of x squared is x cubed divided by 3, and I'm going to integrate that from x equals 0 to 4, and you'll notice again the dx is gone because I've evaluated that integral. I will then plug in the bounds. This is pi times x cubed, my x being 4 for the first case, cubed, all divided by 3, minus pi times my x cubed plugging in 0, so 0 cubed divided by 3. Again, there's a number of different ways we could write this. In this case, this whole term ends up becoming 0, and I'm left with 4 cubed, which is 64 pi divided by 3. And that is the volume of this cone.